Okay, time to get started. So, apologies for missing the last couple of lectures, COVID and all of that. But I'm long since recovered, and very glad to be back in the classroom, getting direct contact with students finally. Here's where we were last. Here's where y'all watched in the recordings too last time. And the big idea of these ideas, one-to-one and on-to, surjective, ejective, however you want to say it, is to build up to this idea of invertibility. That's not the only purpose that these terms serve, of course, but that's my motivation here. So the idea is to point out that, look, for a function to be invertible, let's say this differently. If you want to invert a function, which we need to do sometimes, right, then it better be invertible, right? In other words, all of this nonsense over here, unacceptable. You can't invert something if it's not invertible. So a couple of easy examples, and again, this is just algebra, so I don't want to spend a lot of time on this, but a lot of people mistakenly think that the squaring function, just the regular old, plain old, simple, any number in, any number out, whatever you give me, I'm going to square it, function, that the inverse of that is the square root function. That's what we were all told in elementary school, right? And it's just simply not true. That function's not even invertible. There are lots of real numbers that do not have a square root, right? And there are also lots of real numbers for which there are two square roots, right? So it's wildly not invertible. You can fix both of these issues just by restricting the domain and restricting the target. Now this function, at a casual, careless glance, it looks like the same function. It's just x squared. But again, that's focusing only on the rule of assignment for the function. It's not paying attention to the very important selection of domain and target. This function here is invertible, and its inverse is the square root function. All right. So likewise with inverse trig functions, very commonly misunderstood. I saw some weird, in retrospect, weird stuff when I was in high school that was completely outrageous. This is what I like to call the invertible sine function. So this function here, I'm going to note that this is the relevant part of the graph, says if we look just at these angles, which on the unit circle is like this, right? And if we look just at these output values, which on the unit circle looks like that, then this function, invertible. Right? With that domain and that target, that is an invertible function, and the inverse is called arc sine, right? Which we write like this. And what's cool about this to me is that either one of these pictures, whether you want to look at the graph of this function or whether you want to look at sort of the motivating geometry of this function, namely the idea that you correlate an angle to its y-coordinate on the unit circle. Take your pick, right? But either one of these is a perfectly acceptable picture of sine, but it's also a perfectly acceptable picture of arc sine, suitably interpreted. Right? Because let's take arc sine. Arc sine says you give me a y-coordinate. I want to know what is the corresponding angle. So, cool, no problem. Picture. Right? Likewise, over here, now we're accustomed to this arbitrary and really not essential convention that inputs are always the horizontal axis and outputs are always the vertical axis. And if you insist on that, point of view, then sure, I guess this isn't a picture of arc sine. But there's no particular reason that we have to have, you've got to have the inputs horizontal and the outputs vertical. Right? You can view the input as being the vertical and the output being the horizontal, and then this itself is a picture of arc sine. Okay, all right. Okay, now a little bit of terminology, and I'm going to go super fast through this because it's just terminology. Take the time necessary to read this well enough to make sure you're comfortable with all this. But when you have a function with possibly several inputs and possibly several outputs, just look at how many outputs you have, and depending on whether there are just one or possibly several outputs, we describe the resulting function as being either real valued or vector valued. The idea of vector valued being that when you have several outputs, another way to say that is that your output is a vector with several coordinates. Okay. All right, so that's just a little bit of terminology. And then likewise, you can look at the number of input variables, which again could be one, could be several. Those inputs are the variables, right? The input variables, but whatever. So if there's only one input, then we call it a single variable function. And if there are several inputs, we call it a multivariable function. Okay. All right. Now, there is a temptation to mistakenly believe that as we get into these more complicated structures of functions where you might have several input variables, you might have several output variables, that it's increasingly sort of abstruse and obscure and rare and ivory tower and stuff like that, and nothing could be further from the truth. These kinds of functions, vector-valued multivariable functions, are just literally, they're everywhere. This is not a weird, rare, niche kind of a topic. So my favorite example along these lines is talk about the weather. Again, the most trite of trivial conversations, right? Sit there and talk about the weather, right? And yet, if you think about it, discussing the weather, you are discussing a vector-valued multivariable function because there are a bunch of output variables, namely, right, a bunch of stuff to talk about concerning the weather. And what those are depend on multiple input variables. It depends on where are you. Weather in Durham is not the same as the weather in, San Francisco. And how high off the ground are you? The weather here at basically ground level, very different from the weather at 30,000 feet. Right? And depends on time, right? The weather last week is not the same as the weather now. So intrinsically, very naturally, vector-valued multivariable function, even when you're talking about a trivial matter, a trivial conversation. I think it's an impactful example. Okay. All right, so we're going to talk about how to visualize these kinds of functions, and this is what I'm going to call a sneaky subject here. This is going to seem super easy because there's no nasty algebra, there's no sophisticated constructions, there's no calculus in it, right? This is just going to be a matter of writing down some formulas that you've probably all seen before in some form or fashion, right? And so it is easy it's easy to mistakenly view this as being easy material, and this is not true. This is material that a lot of students have a lot of trouble with, and it's costly to have problems with this material because there are subtleties involved here that are really, really important. And I have seen this over decades that students will kind of blow off. Who cares? This is some trivial, who cares distinctions that are actually really, really important distinctions. And they blow that off and they go right into the stuff that seems hard, and they go to the wrong place because they didn't take seriously the little subtleties about the relationships that we're going to start talking about now between functions and the pictures that we use to represent them. So please do not underestimate these ideas. The key points here are being careful, being precise with your language, being precise with interpretations, and just be aware that if you're anything less than quite precise about this, then you're going to inadvertently write down a bunch of garbage. That's going to lead you to getting wildly, dramatically wrong answers. Right? So please do take this very seriously. And I should mention, another thing that makes a lot of this hard is a lot of high schools kind of condone sloppiness on these important distinctions with subtle but powerful consequences. And so a lot of high schools let you kind of blow this off. So a lot of y'all probably have a bunch of bad habits developed. It's not your fault, right? But nevertheless, we got to fix it. And so just be aware that as you try to take this very seriously and worry about the distinctions and the subtleties, and as you try to regiment yourself to, so that you can avoid all the problems, you will be fighting against bad training. Not all of you, but some of you will be fighting against bad training that you got in high school math classes, where they're very sloppy about this kind of stuff. Okay, so let's talk about graphs. Right, and I'm going to go straight down here to the first example of, here's a graph of a function, right? Yawn, boring. We've seen that picture a million times. It's, graph of a function, it's a curve in the xy plane. Of course it is. That's just how that works, or something. So let's be really careful about this, though. The idea of a graph of a function says we're going to do the following. We're going to look at all of the possible input values, those input values being, I'm going to call them x, so maybe x1 through xn. We're going to look at the corresponding output values. I'm going to call those y. Those are the output values that land in our m. And therefore, of course, there are m such coordinates. The idea of a graph is I take all of the inputs, all of their corresponding outputs, and I smash all of those coordinates together as the coordinates of a single new point, which is, for a given input, this is the corresponding point on the graph. And so the classic example is, given some input value x, in a regular old Calc 1 function, and you look at the corresponding output value y, you kind of smash them together, that output being in the target, and then you take this point x comma y, that is the corresponding point on the graph. I forgot to highlight the y coordinate there. So when you look at all the different inputs, right, you look at the complete collection of all of the points on the graph, then you get this familiar curve. Right? Everybody kind of rings the bells. Right now we are being a little bit more precise and careful about exactly what is this process that we go through to take a function, an abstract algebraic object called a function, and produce the corresponding picture. Right? So we started with a function, we ended with a picture by way of a process. So again, very important to be very precise and careful and explicit about exactly what is that process. Now, before I go on, let me point out there's another way to think about this, very handy in a lot of circumstances, and that is that the graph is what you get when you take your function f, and you choose, not because you have to, you do not have to, but if you make the choice to take your function and decide I'm going to give a name to the output values and think of that output value as being another variable, your single variable function, by that process, creates an equation. There's another distinction you want to make sure to be really careful about. A function is not the same thing as an equation. Right? These are different algebraic objects. Be real careful about that. this equation, if you look at the set of solutions of this equation, then of course you get that same curve. So different way of accomplishing the same thing. So now let's take this idea and apply it to a higher dimensional setting. Let's look now at a function of two variables. Right now, still real valued. One output value. Right. So again, real valued function terminology we just introduced. What do you get when you look at the graph of a function of two variables? Okay, well, let's play the game. For all of the different inputs, for every point, in other words, down here in the xy plane, let's go ahead and put those coordinates in there. We're going to look at the corresponding output value. That's a single value. Go ahead and put that output there. Which again on my picture is going to be like here or something. And then we look at all of the corresponding points. So let's count here now. Let's see, we have two input variables, so that gives me two coordinates on this point on the graph. And then I have one output, that gives me one more, thus a total of three now coordinates in this point on the graph. And that then gives me a point up here in space. So a point on our graph is a point in space. And furthermore, notice that for every point in the domain, it's an entire two-dimensional domain here. For every point in the domain, we get a corresponding point on the graph. You might say directly above it, right? So you can kind of geometrically think of this process as it's just a way to visualize it geometrically, but it's like we're taking this entire three-dimensional plane and every point gets lifted up, but every point by different amounts. And thus we get a also two-dimensional surface that is that graph. Yeah?
Can you only move from more coordinates to less coordinates, like R2 to R1?
Nope. No, you can go from R1 to R2. Yeah, that's right. You get a different kind of a picture. Yeah, that'd be a weirder thing to look at a graph of. It's pretty rare for us to look at a graph of a function from R1 to R2, but there's no reason that you can't do it. Yeah.
What would a graph look like of a function from R1 to R2?
I'm not go. Let's talk about that in office hours. That's I just don't want to go down that road right now. But it ended up being a curve for whatever that's worth. But it's a weird curve, and it's a strange road to go down. Okay. Everybody okay with this example? Okay, so, all right, well, I'm going to say there's something really satisfying about this in the sense that it's kind of, one dimension higher, right? But there's a lot of analogy between the classic single variable graphs that we've seen previously and then this new kind of multi-variable graph picture that we're seeing here. But I claim that we are flirting with catastrophe. Because now let's just take it one step farther. Just one measly little step farther. Let's look now at a function that has three input variables. Okay, well, three input variables and one output variable. Let me say that a little bit differently. The second most trivial possible number of inputs for a multivariable function, and the absolute most trivial number of outputs possible for a multivariable function, right? This is just barely more than the most trivial example, and yet count them up. Now we have a total of 4 coordinates. That means that this picture, if I could draw it, would be a picture of some sort of a structure in 4-dimensional space, and I can't even fake being able to draw that picture. Crash and burn, right? Catastrophic failure of this construction. Doesn't help us at all because we're too low dimensional, we just can't visualize that kind of stuff. So that is really unfortunate. And this is what I'm going to call a massive drawback to the idea of graphs as being a way to understand multivariable functions. There's barely any circumstances where you can, in any sense, even pretend to be able to draw the graph of a multivariable function. This is the primary one. And even here, I'm kind of faking it, right? This is not a three-dimensional picture. There's nothing behind the screen there. It's not actually three-dimensional at all. Pretending. I'm trying to fool you into believing I've drawn a three-dimensional picture here, right? So even this is pretty sketchy. Okay. All right. Okay, so we're going to need more than graphs. And this leads me to one of my really big points. This is a huge point right here. Please do not conflate a graph of a function with the function itself. Right? This is a great example. I could write down formulas all day long, something like this. Let me use a better color choice. Something like this. Right? That is a perfectly reasonable function to talk about. Right? But the graph is a totally different thing. So I can write down, highly multivariable functions effortlessly, no problem. But the pictures, not so much with the graph. So if you view a function as being the same as the graph of the function, then, well, for one thing, you're going to kind of start conning yourself into believing that that there is no such function because there is no such picture, and that's just wildly wrong. Okay. So, in fact, we are going to find many other kinds of pictures to help us understand functions. Graphs are just one of several different kinds of pictures that we're going to draw that in their different circumstances will help us understand, help us get some sort of geometric intuition for how to visualize functions. Okay. Alrighty. So here's another one. It's what I like to call the literal picture. I kind of made that up. I am actually not entirely clear if there is a standard name for this kind of a picture. I think literal kind of gets at the point here, though, and that is that, look, when you have a domain and a target, that's the domain. I'm just going to literally draw a picture of the domain. There it is, R3. Yeah, there's a picture of R3. Best I can do anyway. And if the target here is R1, okay, there's literally a picture of R1. And what does a function do? Well, it takes points out of the domain and plops them down into the target. And so that's kind of what I'm trying to represent here. I take this point here and I can imagine plopping it down in the target like so. So this is about as literal as I know how to get in representing the story of what this function is doing. Right? It's taking points like this one over to image output points like that one. So there you go. It's a picture. Not a very good picture. I'm not happy about this picture. Let me criticize. Let me whine about what I don't like about this picture. Where's the shape? Right, you look back here and you look at all these cool shapes that we saw, and there were fantastically powerful rules that we developed back in single variable calculus that certain geometric features of this shape, like the slope and the concavity, tell me algebraic properties of the function. Namely, the derivative, what's the value, is it more, is it less, is it positive, is it negative? Right? So this picture was fantastic. I can see it. I feel like I'm seeing the whole function in some sense. And, case can be made that, certainly for every input down here, I haven't drawn all of R1, obviously. But it's as if I'm seeing the entire picture of sort of everything that's going on with that function. And no such satisfaction here. Right? So this seems like a bad picture. And this is an apples and oranges comparison. It's completely unfair. I was letting the graph construction be judged on the basis of a really easy function with only one input variable, and I'm judging this literal picture on the basis of this much harder function to deal with, namely one with 3 input variables. So let's be fair about it, and apples, and let's compare this picture of a function from R3 to R1. Let's compare that with what the graph was able to do for a function from R3 to R1, which was nothing. I can't even draw that. So, abject faceplant failure versus kind of leaves a little something to be desired. That's much better. Does everybody see my point there? Right, it's really, really nice. And in fact, this is going to be a super picture for some of our purposes, because even though, I can't see the entire function in any sense, it is still true that I can see something, and I can, for example, ask the very reasonable question: if I were at this point, and by the way, there is its output, corresponding output, I could ask the very reasonable question of, okay, if I were to take off and start moving with some velocity in the domain, if something were to change, in other words, which, by the way, happens all the time, right? Things change all the time. If my inputs start changing, I can ask, how does the output change correspondingly? Now, how you do that calculation, we'll talk about that in a couple days. I forget exactly, but coming up pretty soon. But the details aren't the point here. The point is, I have a picture of the question here. Very reasonable question. This point, if it were to start moving, its output would be moving also, and given that velocity, how do I understand this velocity? Perfectly reasonable picture of the question. And again, as opposed to failure. Okay. So this is actually a pretty great tool. Underappreciated, I think, means of drawing a picture to help you visualize it. Okay. All right, let's talk about level sets. And again, here's a bunch of sort of strict legalese. How do you write? What's the strict definition of a level set? The big idea of a level set, let's look at this picture down here, is we're going to pick an output value, for example 1. Whatever output value you pick, we're going to look for all of the corresponding inputs, the pre-image, you may recall that term from last week. We're going to look for all of the corresponding input points that, when you put them in, give you the selected output. And you can write this down with an equation. Let's see here. So given this output value of 1 arbitrarily, there's 1. And I want to look at all the x's and y's that make the value of the function equal to that selected output value. Right, so given 1 is my output, looking at this function, x squared plus y squared, we're going to set the value of the function equal to this selected output value and see what you get. And of course, that is not a hard geometry algebra problem. This is kind of, flashbacks to high school algebra. I think they would have called this algebra 2 when I was in school. Who knows what they call it now. But of course, that equation, x squared plus y squared, is 1. Boom, circle. So that is an example of a level set of that function. And you can do this for as many output values as you want. Let's do this for the output value 2. Okay, cool. So we're going to set the value of the function equal to 2, and that will give us another level set. Again, a circle. conveniently. So what we have is a means of selecting as many output values as I want, right? And for each one, I get a corresponding, in this case, curve that we call a level set. And the more outputs you pick, the more curves you pick, and the better your picture is. Yeah.
So when we've been defining planes in the homework, we're basically just creating level sets.
They are level sets of functions of 3 variables. That's absolutely right. Yep. Yep. Yes.
I'm confused with the definition of pre-image, because is that the inputs like that can happen, or the actual?
It's all of the inputs in the domain
Okay.
whose outputs are a given selected, whatever the object of the term pre-image. Yeah. Right. Okay. So there you go. You have a couple of level sets. Now I'm going to show you some more hopefully relatable examples. And so here's one. This is actually a pretty common situation to use the level set construction, and they don't use that term. But when you go hiking, if you're walking around in the mountains or something like that, you'll look at what they call a contour map. Or a terrain map, or a topographical map. They have all these different words, right? But it's, in fact, just a picture of a bunch of level sets. So we're looking at the altitude function. And the altitude function, we can talk about level sets by saying, okay, well, let's take a particular altitude. Yeah, I don't know, 300 feet. Which I think is about what we're at here, by the way. But let's take some particular altitude and then ask what are the corresponding points, which when I ask what is their altitude, I get that answer, 300 feet, and that would be some curve. So that is the collection of points in this little picture that I've got that are at an altitude of 300 feet. And you can keep going. You can say, okay, well, yeah, but what about 400 feet? What are the points in the domain that have an altitude of 400 feet? And you get some other curve. And you can just keep going. Just enter, think about however many different altitudes you want. Every altitude has a corresponding pre-image, namely points that are at that altitude, and you get a topographical map. So I'm going to show you a real example here of a topographical map. So I got this from some government website, I've forgotten, USGS or something like that. And this is a topographical map of a mountain that I climbed when I was about y'all's age or so. So something I'm a little bit familiar with. And what's interesting about this is you can see the utility of what is in fact a bunch of level sets, right? Because of how it helps you kind of see the picture. I can kind of see the mountain, and I can see what the trail is going to be like by sort of inferring from the picture here. And so let's start down here at the bottom where you're going up the trail down along in here, and keep in mind now each one of these lines is a level set. Each, by the way, the convention on this particular map seems to be that each line, each separation of two lines represents 40 feet of altitude. Arbitrary, whatever. So each line is 40 feet. And you can see as you're hiking along here, right, you can see that, well, there's a pretty substantial distance on the map that you have to travel to gain 40 feet of altitude. Okay, well, that's a long way to gain 40 feet of altitude. That's not that steep. On the other hand, along in here, it's a lot steeper. A lot steeper because you don't get to drag out that much distance to gain 40 feet of altitude. By contrast, now here you're going to gain 40 feet of altitude over a much shorter distance. So that's way steeper. It's steep enough as to be just downright unpleasant, right? And so, in fact, they don't even make the trail to do that because it'd be too rough. So, where's the eraser? There we go. So they do what are called switchbacks. And you notice the idea of the switchback is that, well, sure, you're still going to get from there to there, but instead of going basically straight up the mountain, oh, that's hard. You can see that you're kind of going at an angle, and instead of having to gain 40 feet over a very short distance, you get to stretch that out because of the angle. And of course, that makes you go the wrong direction, so you have to switch back and go the other way, and then you have to switch back, and you kind of zigzag your way along, and it's a lot more tolerable of a hike going along switchbacks. Does that make sense? You can also see that it's just bonkers steep along in there. That's just crazy. That is so steep that, by the way, when you stand there and look down, you're going to be convinced that it's straight vertical. It's not. It's like 75 or 80 degrees. It's really steep, right? But again, when you're up there and you're like, that's 1,200 feet down, oh my God, you're going to be thoroughly convinced that you're looking straight down. And again, you can see that on the map because of how close these contour lines, aka level sets, are to each other. So tremendously communicative information about the topography of the area. You know, what are you up against in terms of your hike, just from looking at a bunch of level sets, and very handy. Okay, now here's what would be better, hypothetically. A graph definitely be better, because then you can actually see, right? But if you think about it, the problem with using a graph in this situation, and going back here to this picture, if you had two input variables, namely we're walking on the surface of a two-dimensional planet, and altitude, of course, is one variable. Now I've got a total of three variables. That means my graph is a three-dimensional thing, and I would have to walk around with this scale model kind of thing, and it's super bulky. I can't carry that around, right, while I'm trying to do a hike. Whereas topographical map is two-dimensional, fold it up on a piece of paper, put it in your pocket. It's fine. Is that good? By the way, the weather, also, this is an example of level sets. Y'all probably seen pictures kind of like this before, and now let's talk about this line here, this curve there that is sort of the border between places that are in the 50s and places that are in the 40s. What temperature is it that's the sort of the border between the 40s and the 50s? Well, 50. So this curve right here is where temperature equals 50. That is a level set of the temperature function. And then likewise, here, that is where temperature equals 60. So again, not perfect. And if I were to ask, okay, you know, inferring from the picture, what temperature is it in Durham, which I think is probably about right there. So, ballpark, close enough. What's the temperature there in Durham? Well, I don't know exactly. I don't have a level set that's cutting right exactly through where we are. But, you know, I can kind of ballpark it. It's in the mid-50s. Pretty much, I'd say maybe 54 if I had to guess, right? Seems a little closer there than it is here. So you get a reasonably useful interpretation, again, from something that you can put on your TV screen or your internet screen, as may be the case. So another useful situation, and again, they don't talk about this as being level sets, but it is in effect level sets. Okay. All right. So, neat fact, even though level sets and graphs are very different constructions, right? We got looking at completely different kinds of pictures. They are nevertheless related in a nice way, and that is that if you look at how you write down the algebra, this is what a graph looks like. So if I were to take a graph and do a horizontal cross-section of that graph, if I were to slice through my graph with a horizontal plane, if you think about it, a horizontal plane would have equation z equals a constant. Right? that's going to take a slice then. And notice what you get is, in fact, a level set. Because setting f equal to z and z equal to c effectively just sets f equal to c. A little quick little algebraic observation. Kind of cool. You can see this in action down here. Here is a function we've talked about before. And we've talked about the level sets. Right? I'm setting the function equal to a constant, so these are level sets. And those level sets are clearly circles, previously discussed. Right? On the other hand, I can talk about the graph. Again, the graph being what you get when you set the function equal to a new variable, as we discussed. The graph, now we have not yet discussed how to interpret what this picture looks like. This is an equation of 3 variables. That's a harder thing. We will pretty soon, and we'll see how time goes today, but we're very soon going to talk about how to infer what this is an equation of. For the moment, I'm just going to assert that that is this kind of bowl-like shape here, like so. Just take my word on that for the moment. And now let's see this, horizontal cross sections. Taking a horizontal cross section, setting z equal to a constant. Again, horizontal slices, like this. And I appeal to your sense of geometry and shape and space that this bowl, if I were to take horizontal slices of it, in fact, I would get these same circles, pretty much. Those same circles that I got as level sets. Asterisk, slight distinction. These circles are sort of suspended up in 3-dimensional space. Points on these circles have 3 coordinates. Just to be fair, points on these circles only have 2 coordinates because they're in the plane. But when I say they're the same circles, what I mean is the x and y coordinates of the points on these circles are exactly the same as the x and y coordinates of the points on these circles. Okay. All right, so that's a cool fact. Do be careful with all of these constructions. It is so easy to conflate these. Again, this leads to catastrophically long answers. This is not a, eye roll, minor. This is not mathematicians being fussy because mathematicians like to be fussy, right? This is we're fussy because we're trying to protect you against accidentally writing down garbage and getting wrong answers, and then your bridge falls down. Right? So this is very, very important. Definitely be careful about the distinctions between these different kinds of pictures. So, for example, I think this is a lovely example. And by the way, for whatever it's worth, I've made exam questions based on this example many times, as y'all can easily confirm if you just look through my old exams. Again, it's all posted online, right? It's all linked from the webpage. This line, L that has that equation, pretty easy to draw a picture of that line. And again, in your mind, you might be thinking, yawn, high school algebra, old news, I remember how that works, I'm good at this kind of stuff, right? Okay, well, wait, slow it down. Because on the one hand, that line is a graph of this function, but it's a level set of that function, and it's parameterized by this function. Those are 3 different functions, which in their different ways, they all represent the same line. So which function should I use? What's the right function for doing, eventually we're going to start talking about calculus and how you can use calculus to infer, information about a geometric object, let's say a line, just to kind of get the ball rolling. Calculus of which function means what on your picture, right? And what we're going to find is that each of these constructions, so for example, the graph construction, there are some very specific what I'm going to call the calculus of graphs, right? And certain kinds of derivatives that you can write down have certain kinds of interpretations if you are looking at a graph. Whereas, on the other hand, there's going to be a calculus of level sets. Namely, if you're looking at a level set of function, again, there's a different calculus that you can write down that will have different geometric interpretations appropriate to you're looking at level sets. Right? So there's this all these different kinds of interpretations. And one of the things y'all are going to have to do in this class is make sure to have a clear partition in your mind between what is the calculus of graphs versus what is the calculus of level sets versus what is the calculus of parametric curves. They're all different. Right? And so if, for example, if you want to use the calculus of graphs, let's just say you want to use the calculus of graphs to understand this line. By the way, calculus of graphs, super cool, neat tools, powerful conclusions. If you want to use the calculus of graphs, you've got to know to use this function, not that function, not that function. And if you apply the calculus of graphs to this thing I'm calling G, you're going to get, again, just horrible nonsense as your answer. Does everybody see why this is so delicate now? I mean, it's really sort of easy to mess this up. Right? It's super easy to mess this up. And all you got to do is be clear on the distinctions. What is the difference, strictly speaking? What is the difference between a graph and a level set and a parameterization? Right? And make sure to keep clear partitions between calculus and these different kind of geometric constructions. And then just be careful as you solve problems to interpret strictly according to the rules, and everything will be fine. Right? But you do have to be careful in those ways, and don't underestimate this as being we're just moving around easy. You know, the algebra here. I mean, look how easy it is to show that this is a graph. I can show that the line is a graph of this function by just saying, well, I'll set it equal to y, and then I observe that algebra and this algebra are equivalent. And so, sure enough, this is a function whose graph is that line. And the algebra, trivial. This is, borderline middle school algebra, right? You multiply by 3 and you take this term to the other side. I mean, it's just easy algebra. But don't make the mistake of thinking that this is the right function down here, right? It's very easy to look at this and that and think, hey, look at that. That's clearly the right function right there, isn't it? No, that's what you get when you do the level set construction. So the calculus of level sets applied to this function would tell you about the line. But if you apply the calculus of graphs to this function, you get hot garbage. Everybody with me? Okay. All right. Okay, couple minutes left. We already talked through all that stuff. This is just a cool observation. I'm going to do this page quickly. It's pretty straightforward. If you are looking at some surface, let's call it represented by this algebra, I'm going to put a big S right here. So there's some surface S that's described by, I'm going to say this equation, because let's face it, these two equations are morally, come on, you take this, you move it to the other side. They're practically the same equations, right? Okay. Well, what function can I do calculus to understand this surface? Well, you got a couple options. You can notice that as phrased with the top equation, you can view this as being a graph. Specifically, it is a graph of this function. right there. And you can apply the calculus of graphs to that function. Or, now, perfectly free, instead to say, hey, yeah, but the same equation, if I just play with it just this little bit, now I'm viewing it as being a level set, but it's a level set of, what is it that I've set equal to a constant? Well, that's this function. This thing I'm calling g down here is a really different function from that thing I'm calling f up there. Not the same function. Right? So again, be careful, but another way to think about this is if something comes to you written as a graph, and maybe they just straight up give you the equation, or maybe they say S is the graph of the following function, something like that. But if you decide you want to use the calculus of level sets, all you got to do is say, okay, well, this is what it means to take a graph of f. This little algebra right here is trivial. Nothing happened in this algebra. Now, though, because it's written slightly different, I can reinterpret this as being literally a level set of what I can now identify as this different function, and you can apply the calculus of level sets to this instead of applying the calculus of graphs to that. And here's an example of that in action. And you can see this, again, pretty nothing to it little algebra there, right? Yawn, boring, basically the same equation, right? But this function is a function whose graph is what we're talking about. But I can instead apply the calculus of level sets to that function and make an inference about the surface that came to me as a graph, but I can treat it as being a level set of something else. So, valuable little trick, and tragically this only goes one way. Every graph is a level set, but not every level set is a graph. Easy example, this is clearly a level set. It's also clearly not a graph because I cannot solve for either x or y. Okay, all right, so we draw the line right here, and good to be back. See y'all on Wednesday. Have a good rest of your day.